Study Notes with Hamdan. Today, we're diving deep into one of the most fascinating areas of physics, gravitation, planetary motion, and Kepler's laws. Together, we'll explore the forces that govern everything from the motion of our planet to the way galaxies move. So, whether you're here for a quick refresher or a full breakdown, let's get into the heart of how gravity shapes the universe. Ready? Let's dive in. Section 1. Planetary motion and gravitation. In this section, we'll explain freefall acceleration and the gravitational force, Kepler's first, second, and third law. What is Newton's law of universal gravitation? Newton's law states that every particle in the universe attracts every other particle, like how the apple was attracted to the earth. And on this basis, all objects in the universe were attracted to each other in the same way the apple was attracted to the earth. This law also states that since it states that every particle attracts every other particle, it attracts that one with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Let's note, F equals G m1 m2 divided by r squared. What are these values? F is the gravitational force. m1 and m2 mean mass 1 and mass 2 respectively. R squared means the distance between centers of masses squared. And what is G? G is the universal gravitational constant. And it is always a constant, denoted by 6.7 times 10 power of 11 Newton per mass squared over kilogram squared. What is G? G is the constant of universal gravitation. It was determined experimentally by Henry Cavendish in 1798. This value is an example of an inverse square law. Now let's explain Newton's law of gravitation. This gravitation exists as a force of mutual attraction between any two masses, or the center of these two masses. This gravitation is independent of the electrical, nuclear, or any type of property of the objects. This gravitational force is directly proportional to the product of their masses, but inversely proportional to the square of a distance between their centers of the mass. An object that is twice as massive will produce a gravitational force twice as great, and doubling the distance will decrease the gravitational force by a quarter. Let's explain why. Since F equals 1 over r squared, our gravitational force equals the inverse of the square of the distance. So we can say that if we increased force by 2 times, then it also happens that r will decrease by 4 times. So r will decrease by 4 times. Let's say if r increased by 3 times, then force will decrease by 1 over 9, or tripling the distance results in a 9-fold decrease in gravitational force. Let's move on. What is the universal gravitation? It means that force that mass 1 exerts on mass 2 is equal and opposite to the force that mass 2 exerts on mass 1. Let's see. So we have here two balls. The first ball exerts a mass on the second ball. So the force starts from the centers of these two objects. It always does. This is a law. So this law states that the force, or F21, equals or is directly proportional but opposite to F12. This is a direct example of what we call Newton's third law, or action-reaction pair. Let's move on. Let's start with an example. Let's use the equation that we learned of Newton's law of gravitation to solve the following question. Two masses, 50 kilograms and 100 kilograms, with a 2 meters distance between their centers. Let's find the gravitational force between them. We are going to use this law. Fg equals to G m1 m2 over r squared. Given that, let's state the givens first too. So we have m1, which is 50 kilograms. Note that the kilogram is the SI unit. We have m2, which is 100 kilograms. And we have r, which is 2 meters. Note that meter is the SI unit here. And we also have a constant. You should memorize it, which is G. It never changes. It's 6.67 times 10 power of negative 11. Now, let's substitute all of these values in the equation to find the answer. So, Fg equals to 6.67 times 10 power of negative 11 times 50 times 100 divided by 2 squared. We get that 8.3 times 10 power of negative 9 newtons. So even though this force is a very small fraction of this force is a very small, but it still shows that gravitational exists even in the smallest amounts between two objects. Let's go to the second example. Let's predict the gravitational force between two 15 kilogram balls whose centers are 35 centimeters apart. Let's use the same equation. Given that M1 is 15 kilograms, M2 is 15 kilograms, and G is the constant of 6.67 times 10 power of negative 11. But why did they give us R here 35, but in the givens we have R 0.35? Note that the SI unit of R, or we could call it that distance, is always meters. So when they give you in centimeters, we have to convert to meters by dividing by 100. So 35 divided by 100 gives us 0.35 meters. Let's move on. So once we have all of the givens, let's substitute them in the equation. Fg equals to G M1 M2 R squared. So substituting gives us 6.67 times 10 power of negative 11 times 15 times 15 over 0.35 squared. This gives us Fg equals to 1.2 times 10 power of negative 7 newtons. We note that also in this example the gravitational force is so small, but this also proves Newton's theory that gravitation exists everywhere, even between two pencils, even between two 15 kilogram balls. Let's go to the second slide. Let's explain the gravitational force between objects. We need to note this relationship. Let's use the same equation, which is F G M1 M2 over R squared. If the distance between the two masses is doubled, what happens to the gravitational force? The gravitational force decreases to 1 over 4. Why? It tells us that the distance is doubled. What happens to the gravitational force? What kind of relationship do we have between F and R? F is inversely proportional to 1 over R squared. So let's say the distance is doubled, then this causes that F will decrease to 1 over 4 of its original value. Let's solve the third question. If the distance between the two masses is tripled, what happens to the gravitational force? This uses the same relationship from the previous question. F is inversely proportional to 1 over R squared. So if 1 over R squared increases by triple or 3 times, then that means that F, so you could just take the 3, square it, and then that value F decreases by 1 over 9, or F will become 1 over 9 of its original value. Let's solve the fourth question. If the two masses are doubled, what is the effect on gravitational force? So what is the relation? So what do we have here? Mass and gravitational force. They told us that if the two masses are doubled, what happens to the gravitational force? We have the relationship Fg equals, or inversely proportional to m1, m2. So it is directly proportional to the masses. So if the two masses doubled, or 2m times 2m, or we could say 4m, then f increases by 4f, or it becomes 4 times of its original value. These questions explain to us the relationships between the various variables in this equation, between gravitational force and mass, between gravitational force and distance as well. Let's move on. Let's use the same equation to answer the two last questions. If the distance decreased to a half, what is the effect on gravitational force? So, if distance, f, since f is inversely proportional to 1 over r squared, so if distance decreased to a half, what is the effect on gravitational force? So, if 1 over half r squared, then it becomes 2 over r squared. So we just square the 2 and f will increase by 4. Since 2 squared is 4, so f will increase by 4. Since it's inversely proportional and distance decrease, so f will increase by 4f, or 4 times its original value. Let's see from the following graph what is the relationship between force, or f, and distance, which is r. See, it is inversely squared, or it has an inversely proportional relationship. That is an always constant relationship between these values. Let's move on. Let's solve a question. These two balls have their centers 2 meters apart. 2 meters, or these centers are 2 meters apart. As shown on this figure, one ball has a mass of 8 kilograms, another ball has a mass of 6 kilograms. What is the gravitational force between them? Let's solve. Since F equals to G m1 m2 r squared, then we could say that equals to 6.67 times 10 power of negative 11 times 8 times 6 over 2 meters squared. That gives us 8 times 10 power of negative 10 newtons. So the gravitational force between these two balls is 8 times 10 to the power of negative 10 newtons. Let's solve. These two bowling balls have a mass of 6.8 kilogram. They're located next to each other with their centers 21.8 centimeters apart. What gravitational force do they exert on each other? All of these equations follow the same rule. F equals to G m1 m2 over 2 over r squared. Let's solve. So F equals to 6.67 times 10 power of negative 11 times 10 power of negative 11 times 6.8 times 6.8 over 0.218 squared. Why did we put 0.218? Because we converted 21.8 centimeters to meters. So that results in 6.5 times 10 power of negative 8 newtons. A relatively small gravitational force, but it still exists. Assume that you have a mass of 50 kilograms. Earth has a mass of 5.97 times 10 power of 24 kilograms and a radius of 6.38 times 10 power of 6 meters. What is the force of gravitational attraction between you and the Earth? So this is you, this is Earth, this is you. There you need to describe the relationship between the center of you, yourself, and the center of Earth. Since you are on the top of the Earth or on the crust, so the radius from the center of the Earth till you is 6.38 times 10 power of 6 meters. So the values that we have is distance, we have mass of you, of the person, and the mass of Earth. Let's solve. F equals to 6.67 times 10 power of negative 11 times 50 times 5.97 times 10 power of 24, and the distance 6.38 times 10 power of 6 squared. Let's solve. If we solve all of this, we get the F equals to 489 newtons. So the force of attraction, gravitational attraction between you and Earth is 489 newtons. What is your weight? How could we calculate that? We know that gravitational force or weight is also calculated by Fg equals to mg. So we could say that, but what m should we choose? Your weight. So we would take the mass of the person. So 50 times 9.8 equals to 4.9 times 10 power of 2. So is the gravitational attraction and the weight relatively same? Yes, so the answer is true. Let's calculate the gravitational force between two electrons that are 1 meter apart. They told us that the gravitational force between two electrons are 1 meters apart, but the force is 5.54 times 10 power of 71. We need to find the mass of an electron, or for one electron. We could use that. We do have the same equation, F equals to G m1 m2 over r squared. Let's substitute, where m1 equals to m2, so we would use m squared. So we could use m squared equals to f r squared over g, or m equals to the square root of f r squared over g. Substituting those values, square root 5.54 times 10 power of 71, or negative 71, we forgot the negative here, times 1 meter squared, over the gravitational constant 6.67 times 10 power of negative 11. We get that the mass of a single electron is 9.11 times 10 power of negative 31 kilograms. So we found that even the smallest atoms, or even the parts of an atom like an electron, do exert gravitational forces between each other. Let's solve this question as well. A 1 kilogram mass weighs 9.8 Newton on Earth's surface. The radius of Earth is roughly 6.4 times 10 power of 6 meters. Let's calculate the mass of Earth. So we have this equation. Let's manipulate it to try and find the mass of Earth. Since we do have one mass only, so we could use this equation. F equals to G m over r squared. Or we could manipulate it. Not this equation. We would manipulate it since we have m1, which is 1 kilogram, and we have m2, which we need to find the mass of Earth. Or we could say that's me. We would say that me equals to f r squared over to g m1. Substituting these values gives us 9.8 newtons, 6.4 times 10 power of 6 squared over 6.67 times 10 power of negative 11 times 1. So this gives us 6.0 times 10 power of 24 kilograms. So this value is the mass of Earth. Let's solve one last equation before moving on to the next topic. Two spheres are placed with their centers are 2.6 meters apart. The force between the two spheres is 2.75 times 10 power of negative 12 newtons. What is the mass of each sphere if one sphere is twice the mass of the other sphere? Let's go. So F equals to G m1 m2 over r squared, where m1 equals, or let's say m2 equals to 2 m1, since m2 is twice the size of m1. So we could say as well equals to f equals to g m1 and 2m1 over r squared. We need to find m1, so we could say that m1 equals to fr squared over 2g. So then we substitute the values. 2.75 times 10 power of 2 and negative 12 times 2.6 squared. Then 2 times 6.67 times 10 power of negative 11. Then we calculate it to be 0.37 kilograms. Since m2 equals twice m1, so to find m2 we need to just multiply to 0.37, which gives us m2 results in 0.746 kilograms. So this is the mass of m2. Now let's talk about an interesting topic called free fall acceleration. Often we hear that astronauts are weightless in space, but is there really no gravity up there? It is true that actually astronauts are in free fall around the Earth, giving the sensation of weightlessness, but gravity is still acting on them. Since weight equal mg and weight is 0, g is 0, but since weight is always 0, we might think that g is 0 or they do have no mass. This is wrong. Let's say we stand on a scale in an elevator and the cables are cut, so the elevator will be falling. You will weigh nothing since you're in a free fall, but this does not mean that g equals 0. Even on Earth, we experience free fall acceleration. This acceleration depends on the distance from the Earth's center, which is why it changes slightly with altitude. Let's calculate free fall acceleration and the gravitational force. Let's consider an object of mass m near the Earth's surface, or we could say a satellite. It has an acceleration ag, or ag could we also say gravitational acceleration, which is due to gravity. Since mass of Earth is 5.9742 or 6 times 10 power of 23 kilograms, and r, or the radius of Earth, is 6,378.1 kilometers, we could find that acceleration of gravity due to Earth's surface is always 9.8 meters squared. Free fall acceleration and the gravitational force. Let's say that the object is not on Earth's surface, then it would be also affected by another attribute, which is height. So we need, since radius now consists of the radius of Earth plus the height of the object, or we could say satellite. This gives us the total r. So to find r, it is re plus h squared. And ag will vary with altitude due to the presence of an unconditional variable h. Let's use the free fall acceleration we learned, or the gravitational field. The strength produced by an object is equal to the universal gravitational constant times the object mass divided by the square of the distance from the object center, where m is the mass of the object, r is the distance between the point and the object center, g is always the universal gravitational constant. M could be a planet, a ball, satellite, a pen, or any object when we relate it to another object. Okay, let's solve free fall acceleration relationships. From the equation, what happens to g if r increases? Since in relating from this equation, g is is inversely proportional to 1 over r squared. So if r decreases, then g increases. I mean, if r increases, then g decreases. What happens to g if r decreases? Since we follow the same relationship, then if r decreases, then g increases. What happens to g if r doubled? It will decrease by 1 over 4g. Why? Because r squared. If 2r squared, then it will become 4r, then g will decrease by 1 over 4. What happens to g if r is halved? Since 1 over 2v squared, it will decrease by 1 over 4r, then that will result in g increasing by 4. Let's go on. This picture shows us the gravitational field affected by various altitudes, where it is stronger near the surface of the Earth, but weaker further away from the surface of the Earth. So on the surface directly, we have a value of 9.8. When we keep going away, the value decreases: 7.4, then 4.9, then 2.5, then lastly 0.98. Let's solve. The mass of the moon is 7.3 times 10 power of 22 kilograms. Its radius is 1738 kilometers. What is the strength of the gravitational field on the surface of the moon? We will use this equation, or let's say given these values of moon is 7.3 times 10 power of 22 kilograms. The radius is given in kilometers. We have to convert it to meters. How do we convert kilometers to meters? We multiply by 1,000. We need to find g, and we need to find g, or the acceleration due to gravity, and then we could find g, which is 6.67 times 10 power of negative 11. So we solve using the equation g equal g m over r squared. We have g equals to 6.67 times 10 power of negative 11 times 7.3 times 10 power of 22 over 1,017,38000 squared. Solving this gives us the value of g equals to 1.61 Newton per kilogram. If we want to write what is the acceleration due to gravity, we just need to convert these values to 1.61 meter per second squared. Let's solve. The gravitation force is what? It's an infinite range force. What is a gravitation force? The gravitation force is an infinite range force. Why? It is true because gravitation force operates over unlimited distances. Although it becomes weaker with increasing distance, gravitational never becomes zero, no matter how far apart the two objects are. The acceleration due to gravity on Earth's surface does not depend on the object's mass. Why? It depends on the mass of Earth, or the mass of the central object only. Since we have a planet, this is the center and this is an object orbiting it. We use the mass of the center, we use the radius, and we use the height from the object to the center of the central planet. Solving this gives us the acceleration due to gravity on Earth or on a central big celestial body surface. So the acceleration due to gravity never depends on the object's mass. This is relevant when we need to calculate the acceleration due to a satellite orbiting an Earth. Now let's talk about satellites. It was discovered by Johannes Kepler, a German astronomer and mathematician. He formulated the 3 laws of planetary motion. These laws apply not only to planets, but to any system of a body revolving about a massive body. Let's say a ball revolving around a car. a satellite revolving around Earth, even the moon revolving around Earth, and even the sun when it revolves, even the Earth when it revolves around the sun. Let's talk about Kepler's first law. How can planets rotate around the sun? Which force is being used? So, let's say what holds this planet, or what keeps it rotating in an elliptical orbit around the sun? This is always gravitational force. It's gravitational force between the planet. It's a gravitational force between the planet and the sun. It is always used as a centripetal force since it is always going to the center. So Fc. What are the three laws? Let's talk about the first law. This law states that planets move in elliptical orbits with the sun at one foci. This elliptical path means the distance between the planet and the sun, it's not constant. It changes as the planet moves along its orbit. Let's say the planet is here. The orbit is farther. Let's say the planet was here. Then it will be closer to the sun. So, one foci is always empty, while another is occupied by a large celestial body, or in this case, the sun. Let's talk about Kepler's first law. All planets move in elliptical orbit with sun at one foci, and any object bound to another by an inverse square law, or the one that we took in the beginning of this session, will move in an elliptical path. This also states that the second focus or foci is always empty. This is a constant. Let's answer some questions about Kepler's first law. How many foci are there for an elliptical path? Or we could say, how many technically centers are there for an elliptical path? None. Or 2. We have 2 centers for an elliptical path. How many foci are there for a circular motion? So we have a central system and we have an object that's orbiting it on a circular orbit. How many foci or focus does it have? It will only have one central focus, or one foci only. What is the path of any planet around the sun? Depending on Kepler's first law states that the path is always elliptical. Let's go to the next slide. Let's talk about Kepler's second law. Kepler's second law, also known as the law of equal areas, says that the line joining a planet and the sun sweeps out equal areas during equal intervals of time. This means that planets move faster when they are closer to the sun and slower when they are farther away. Look how when a planet is here, it has the same area as the planets here, but they move slower here since they are further from the sun, but these two planets move closer since they are closer to the sun. But both of these areas are swept at equal areas and at equal time intervals. Let's talk about the third law. Kepler's third law states that the square of the period of any planet is proportional to the cube of the average distance from the sun. This relationship lets us calculate the period of orbit for any celestial body, be it a planet or a moon, based on its distance from the object it orbits. What is the meaning of a period or t of a planet around the sun? Period or time, it's needed for planets to complete one rotation around the sun. Is the distance between the planets and the sun constant? Never, because depending on Kepler's first law, the orbit path is an elliptical path, and an elliptical path never has a constant path. Let's talk about the formula for Kepler's third law. Mathematically, we can define Kepler's third law as Ta over Tb squared equals to Ra over Rb squared, where Ta, Tb equals to Ra, Rb cubed. Kepler's third law, also we need to have the radius, mass, and the average distance from the sun. Let's say the sun has a radius, has a mass, and it has its own average distance. Usually in an exam or examination of these, and including Kepler's third law, you will be given this table or the values that you need to solve any question in the question provided. Now, let's talk about Kepler's third law, or the one that relates to comets. Kepler's law applies not only to planets, but also to comets. Comets follow long elliptical orbits, and their behavior matches Kepler's observations. For instance, long-period comets have orbital periods larger than 200 years, and short-period comets have orbital periods shorter than 200 years. For instance, Comet Macknaght, with a period of 92,000 years, is a long-period comet, while Comet Halley, with a period of 76 years, is considered a short-period comet. Revising on Kepler's third laws, all planets move in elliptical orbits with the Sun at only one focal point. Second law, a line drawn from the Sun to any planet sweeps out equal areas in equal time intervals. And the third law, the square of the orbital period of any planet is proportional to the cube of the average distance from the Sun to the planet. Let's solve a question. Galileo measured the orbital radii of Jupiter's moons using the diameter of Jupiter as a unit of measure. He found that Io, the closest moon to Jupiter, has a period of 1.8 days and is 4.2 astronomical units from the center of Jupiter. Callisto, the fourth moon from Jupiter, has a period of 16.7 days. Using the same units that Galileo used, predict Callisto's distance from Jupiter. We do have Ti, or the time Callisto needs 16.7 days, the time Io needs 1.8 days, and the radius that Io does 4.2 units. We need to find the unknown RC. How could we find that? Let's use the formula that we have, which is Tc over Ti squared equals to Rc over Ri cubed. Or we could say that R cubed equals to R1 cubed over Tc over Ti squared. Since we need to remove this cubed, we would radicalize this by 3, radicalize this whole equation by 3, cancelling the cubed here. Now let's substitute. R equals to 4.2 units or astronomical units cubed multiplied by 16.7 over 1.8 squared. We get R equals 19 units. So Callisto takes 19 astronomical units radius, so it takes a longer time. Meanwhile, Io takes 1.8 days to rotate 4.2 units around Jupiter. Let's also talk about Kepler's third law, that the square of the orbital period of any planet is proportional to the cube of the average distance from the Sun from planet, or T is proportional, or K to A cubed, where T is the period of the planet, A is the average distance from the Sun, and on the length of a semi-major axis. For orbit around the Sun, K is 2.97 times 10 power of negative 19. K is always independent of the mass of the planet, where in this case we always substitute K to be 4 pi squared over G over mass of a planet square mass, where it becomes T squared equals to 4 pi squared over Gm multiplied by the distance cubed. We need to find the mass of the Sun, noting that the period of the Earth's orbit around the Sun is 3.56 times 10 power of 7, and the distance is 1.496 times 10 power of 11 meters. Substituting this in the equation, m times 4 pi squared, distance 1.496 times 10 power of 11 over G, the universal gravitational constant, times the orbit or the time or period, 3.156 times 10 power of 7 squared. the mass of the sun turns out to be 1.99 times 10 power of 30 kilograms. Now, let's solve a question relating to this formula. Uranus requires 84 years to circle the sun. Find Uranus' average distance from the sun as a multiple of Earth's average distance from the sun. Let's solve. Since we do have that R of Uranus is Uranus equals to R, both of them are cubed, of Earth, and the period of Earth squared and the period of Uranus squared. Substituting the values gives us R Uranus cubed over 84 squared, since we have 84 years, equals to R Earth cubed over 1. Why did we substitute 1? Because we need to find the ratio of the distance from the sun as a multiple or ratio of Earth's average distance. So since Earth's distance from sun, its ratio or the period it takes is 1 astronomical unit, or AU. So R Uranus is a multiple equal to 19.2 RES. This is the formula. Now we will talk about universal gravitation and Kepler's law. This equation is specific to the period of a planet orbiting the sun, where a period planet orbiting the sun is equal to 2 pi times the square root of the average distance from the sun cubed divided by the product of gravitational constant and the mass of the sun. Using the previous equation, let's answer the following question. What is the relation between the period and the distance of a planet? Period is directly proportional with the cubic root of the distance. So T is directly proportional to the cubic root of the distance. Does the period depend on the mass of the planet? No, it only depends on the mass of the sun. T depends on mass of the sun and distance. Let's solve a question. Neptune orbits the sun at an average distance given in the picture, which allows gases such as methane to condense and form an atmosphere. If the mass of the sun is 9.99 times 30 kilograms, let's calculate the period of Neptune's orbit. We have the given 1.99 times 10 power of 30, R, which is 4.96 times 10 power of 12, and we need to find the time or period of Neptune's orbit around the sun. Given this equation, T equal 2 pi Q in the square root of R cubed over G and MS, we use this formula, which results in the time being 5.199120307 seconds, which is a huge amount. But since we need to write it in the SI unit, which is seconds. Let's solve a logical question. Picking up a rock requires less effort on the moon than on Earth. How will the moon gravitational force affect the path of the rock if it was thrown horizontally? Let's say, comparing the gravitational force of the moon and Earth, moon has a relatively lower gravitational force. So it will take more time for the rock when it's thrown to reach to the surface of the moon rather than for it to reach the surface of Earth. Let's say, if the thrower accidentally drops the rock on her toe, will it hurt more or less than it will be on Earth? Since rocks will be dropped from the same height, on the moon it will hurt less, since it will have a lower value of Q or G, which is gravitation. That means the rock will strike the toe with a smaller velocity, or it will strike it slower than it will strike the toe on Earth. Let's talk about the speed of a satellite orbiting Earth. If the speed of Earth around the sun increases, what would happen of the Earth? It will divert away from the orbit, because the Earth, the sun, and we have the Earth. Let's say if the speed increases, it will divert away, aka going away from the elliptical path that it has. If If the speed of the Earth around the Sun decreases, what would happen to the Earth? It will come closer to the orbit, since the Earth tends to go outside the orbit, but if that speed decreases, then it will go inside towards the Sun. Note that for any planet that rotates around the Sun or a moon rotating around the planet, there is a fixed speed. Now let's take this formula. The speed of a satellite orbiting Earth. The speed of a satellite orbiting Earth is equal to the square root of universal gravitational constant times the mass of Earth divided by the radius of the orbit, where v is the speed of the satellite, me is the mass of the Earth, r is the radius of the orbit, and g is the universal gravitational constant. Where the same thing, period of a satellite orbiting Earth is equal to 2 pi times the square of root of the radius of the orbit cubed divided by the product of universal gravitational constant and the mass of the Earth. Let's take a final example. Orbital speed and period. Assume that a satellite orbits Earth 225 kilometers above its surface. Given that the mass of the Earth is 5.97 times 10 power of 24 kilograms, the radius is 6.38 times 10 power of 6, what are the satellite's orbital speed and period? Using the given values, let's solve. Let's first determine what is the orbital radius, or r. r equals to h plus re, which is 2.25 times 10 power of 5 plus 6.38 times 10 power of 6, which gives us 6.60 times 10 power of 6 meters. Let's solve for the speed. First of all, the speed is gme over r. Or let's erase this, then write it above here. V equal gme over r, where if we substitute 6.67 times 10 power of negative 11 times 5.97 times 10 power of 24 over 6.60 times 10 power of 6 meters. Solving that gives us 7.77 times 10 power of 3 meter per second. Now let's solve for the period. Now that we have found the velocity, let's solve for the period. Solving for the period, t equal 2 pi r cubed g mass of Earth equals to 2 pi 6.60 times 10 power of 6 cubed over 6.67 times 10 power of negative 11 times 5.97 times 10 power of 24. That gives us 5.34 times 10 power of 3, or that's approximately to 1.5 hours. So the orbital radius of that satellite is the orbital speed. We have found that to be 7.77 times 10 power of 3 meters per second, and the period, it takes about 1.5 hours to orbit around Earth. Let's solve. Using the following equation, let's answer the relationship questions. V equals to g radical of gme over r. If the radius of the orbit increases, what is the effect on the speed needed for the rotating object, or of the orbiting object? If the radius increases, the speed needed will decrease, since if the r increases, the v will decrease, or the speed will decrease. If the radius decreases, what is the effect on the speed needed for the rotating object? Since it will become closer to the Earth, or the mass of Earth, the gravitation will become stronger, so it will need a higher speed to stay on orbit. What factors does the orbiting speed depend on? The orbiting speed v depends on the mass of the planet and the orbit or radius of orbit. Let's answer the following relationships from this equation. If the radius increases, how does that affect the period of rotation? Since t is directly proportional to r, so if radius increases, time will increase. If radius decreases, time will decrease. What factors does the period depend on? It depends on mass of Earth and radius of orbit. So we notice that the velocity and the period depend on the same exact values. Which of the following factors must one take into account when determining the necessary orbital speed for a satellite around Earth, discarding any other type of friction forces in the orbit path? We should only take care of the radius of the orbit. Since we need to find the orbital speed, we notice that V only depends on mass of Earth or R, or the radius, orbit radius. So it depends only on the radius of the orbit. Let's solve. A space shuttle orbits Earth 300 km above the surface. Why can't the shuttle orbit 10 kilometers around above Earth? It's because of much of the shuttle's kinetic energy would be dissipated as heat in the atmosphere, because when a rocket is launched above Earth or away from Earth, the kinetic energy will be dissipated as heat a lot, because it will try to fight the gravitational force pulling it back towards Earth. So it would need to orbit it at a very large or away height. A geosynchronous satellite orbits the Earth with a period of 24 hours so that its motion is synchronized with the Earth's rotation. Viewed by an observer on Earth, a geosynchronous satellite appears to be stationary. Which of the following statements is true about geosynchronous satellites? All geosynchronous satellites with circular orbit, since Earth is circular, so the satellite will have a circular orbit around Earth. So all geosynchronous satellites with circular orbit will have the same orbital radius to maintain the same velocity, to maintain the same orbital period, so it will be synchronized with the Earth's rotation. Let's solve a final question before wrapping up. Two satellites are in circular orbits around Earth. One is 150 kilometers, the other is 160 kilometers. Which satellite has a larger orbital period? We noted that more radius, more period. So the other satellite, which is 160 kilometers, has a larger period. Which satellite has a greater speed? We noted that more radius equals to less speed. So the less satellite, or the one which is 150 kilometer, has a faster speed. The end. Thank you for joining me and learning with us today as we explored gravitation, planetary motion, and Kepler's laws. Remember, these concepts aren't just theoretical, they are the foundations of modern physics, astronomy, and space exploration. As always, keep learning, keep asking, never stop wondering, and see you in the next video.